Okay, welcome back. This is chapter 3. We're going to be talking about variables and constants. So, this entire chapter talks about how to use variables and constants, what they are. And so, your lab assignments will be specifically using variables and constants. Okay, there we go. Always takes me a minute. So our objectives is to distinguish among a variable, a named constant, and a literal constant. Explain how data is stored in memory. Select an appropriate name. Select an appropriate data type. And select an appropriate initial value for a memory location. And declare a memory location in C++. So after step 3, the programmer has an algorithm and has test checked it. The next step is going to be coding the algorithm into a program. So there's a lot of stuff that we've done. We've done 3 steps before we have even started coding. And those 3 steps, like I said before, are really important. So that is what we call the design phase in programming. And typically the design phase counts at 60% of the work. So designing the program is 60% of the work. Actually coding it and testing it, it's going to be the last 40%. So it's a pretty big important step. And you want to think about those first 3 steps like when you're building a house. You can't just start building a house without a plan. So if you're getting a house built, right, you're going to talk to your architecture, and he is going to sit with you, try to figure out what you like. He's going to ask you questions so that he builds exactly what you're wanting to be built. And that part of him talking to you and for him making the drawings and showing them to you and editing those, that takes a long time. And if you get that wrong, at the end, he's going to give you a house that you're not going to be happy with. So that's the same thing with programming. So when we start coding, some of the things that we start thinking about, you did an IPO chart, and in your IPO chart, you had these things called inputs and outputs. So your inputs are the things that are going to be entered, and the outputs is what you're going to display or output in some way. And so those things have to have, they're going to be in memory, and anything in memory has to have a variable. So we begin by assigning a descriptive name and a data type to all our input and our output items in the IPO chart. So we got to give them descriptive names. Sometimes we give them an initial value, sometimes we do not. These are used to store the item in the computer's internal memory. So our variables, our constants are used to store information in internal memory. So let's talk about internal memory. So the computer's internal memory is composed of memory locations, each with a unique numeric address. We're going to talk about memory so you can understand it if you've never understood what memory is like. So each memory location has an address similar to collection of storage bins. Each address can store one item at a time. An address can contain numbers, text, or program instructions. To use a memory location, a programmer must reserve the address called declaring. So let me see what this is here. So I think of I think of memory locations like, think of if you go to, if you have lockers for whatever, whether it's lockers in a school building or lockers for Amazon so you can pick up your packages, or maybe the little mailboxes when you go to the post office. So each one of those um, lockers or mailboxes is has a unique address, a unique number, and it can hold so much, right? So some lockers are bigger than others. Some lockers can hold just a few letters, some lockers can hold big packages. And that's the thing that happens with memory locations, is that we can create small memory locations that hold one number, or a memory location that's very big and can hold um, somebody's name or somebody's address, or um, a large amount of text. So when we are creating the program and we're looking at these inputs and these outputs, we have to reserve a little locker for each, or a mailbox for each separate input and each output. Declaring a memory location is done with an instruction that assigns a name, a data type, and an optional initial value. So this is like saying, okay, I'm going to open a mailbox, and the mailbox has to have a name. It has to have what type of mailbox it's going to be. Is it going to be one that just holds letters, a small one, or do you want a big mailbox where you can receive big boxes? And then an initial value doesn't really apply to a mailbox, but it would be like your mailbox starting with, if they left you a nice welcome package or something, that would be the initial value. Or the initial value can just be an empty mailbox. And typically that's what we do with programming, is we create variables that are empty and have nothing in them. We want them to start out empty. The name allows the programmer to refer to the memory location elsewhere in the program using a descriptive word rather than the numeric address. So each memory location has a numeric address, and it's in a hexadecimal form. And I don't think we're going to be looking at hexadecimals here, but it's in a hexadecimal form. And you don't want, as a programmer, you don't want to deal with hexadecimals and say, the cost is going to be saved in FFE0, blah, blah, blah. You want to say the cost is going to be saved in the variable named cost. And so just like your mailbox might be P.O. Box 3240, it has a name. So Jeanette Serrano has box 3240. And we're going to call each memory location its name and not its actual hexadecimal address. And then the last bullet says the data type of our variable indicates what type of information the address is going to store. So the data type is going to say, well, cost is a number that has a decimal, so I'm going to have to define it as a double data type because it has decimals. My number is going to be a whole number, like an age. You're 1 year old, 2 years old, 3 years old, so on. So that's an integer. What you're going to be storing in the variable, somebody's name. So a name would be a string of characters. And so we have something called data types for each variable or constant that we create. So like we said earlier, there's two types of memory locations that can be declared, either a variable or a constant. And if you have math, you've heard of both of these. Variables are memory locations whose values can change during runtime. So when the program is running, you can change the memory location. So think of a program think of a video game, right? And the video game is keeping how many points you have scored. So the score has to be a variable because the score changes your score is either going to increase or decrease. It doesn't stay the same all the time. So while you're playing, that score is changing. That would be a variable. Most memory locations are variables. Name constants are memory locations whose values cannot change during program execution. So again, if we take the example of a video game, let's say that you're playing a video game where you have a certain number of lives, and if you lose, let's say you have 10 lives, and if you get killed 10 times, your game's over. And so that number 10 of the number of total lives would be a constant, because the number of lives, the max number of lives that you can have is 10, and that's it. So that's a constant that's not going to change. Now your score, your number of lives will change, but the max lives will not change. And we'll have some more examples on constants, but if you think of algebra, some of constants in algebra would be pi. So pi has a specific number. It is a number that doesn't end, but typically we say that pi equals 3.14, and we just assign it 3.14, and that would be a constant because it's not going to change. Some other things that can be constant are things that in programs that they may change, but these are things that can only change every so many years. So it takes a very long time for them to change. And they're things that you want to make sure that that nobody ever messes with, that nobody ever by mistake changes them. For example, like tax rate, the sales tax in all the stores is a constant, and it can only be changed in one certain place, and it only happens when the when the city decides to change their sales tax rate. And so that's something that would definitely stay constant. So here's an example of some of how we can also think of internal memory. So here they have shoe boxes, and they have different sizes of shoe boxes, and depending on the size of the shoe, the box is going to get bigger. That is the same thing as internal memory. So I want you to think of memory when you buy a computer and you're thinking of memory. I want you to think, well, it has a number, it has a limit. Okay, so think of a big house, right? The big house that's how much memory you have. And then you're able to put these shoe boxes in the house. And once you fill up the entire house with shoe boxes, that's all you can get in there, nothing else. And so if you have a pair of sandals, you're not going to put them in this box, although you can, right? You can put them in that box, but then you have a lot of wasted space. That's the same thing with memory. If I choose a data type that's too big for my data, then I'm wasting memory. These days, we don't have to worry a lot about memory because the computers come with a ton of memory, but we still have to be very vigilant, especially if we're writing really big applications, about the memory that we use. So if I have an integer, like I'm going to be storing numbers between 1 and 100, I'm not going to store them in a memory location that holds big numbers like this with decimals. I'm only going to choose something that holds integers. So here we have different memory locations. This is one that's holding a decimal. This is holding also a decimal. This is holding a string. And this is holding either a Boolean, either true or false. So selecting the name for your name from your memory location, it should be a name that is descriptive. So if you're calculating the cost of let's say the the total cost of your purchase, then you want to say maybe purchase cost. If you're calculating the area of a square, then call your variable area of a square. Don't just call it A, B, C. Actually give it, or just call it area, but say area of a square. Let's see here. The name should help the programmer or other programmers remember and understand the memory location's purpose. It should be as short as possible while still being descriptive. So we don't want super long names, okay? And then short names are easier to read and result in more concise code. There are some rules for creating variable names. So look, if you look here at the very bottom, here's a variable name called discount. So, it tells me, I know exactly what it is. It's discount, and it's short, it's descriptive. So let's look at the rules for actually creating a name. The name must begin with a letter and can contain only letters, numbers, and underscore characters. You cannot have punctuation marks, you cannot have spaces, you can't have other special characters like a $sign or a %sign. It cannot be a keyword. So a keyword in C++ or any language, keywords have certain meanings. So if I, in certain languages, if I use the word print, print is a keyword, and it means I'm going to print out to the screen whatever string or value I want to print. So there's going to be keywords you're going to be learning. So it cannot be a keyword. And the names are, names are case sensitive. So if you decide to name your variable with a lowercase d, then this variable is different than this variable. So if you name the variable discount like this, and you reference it somewhere else like this, it's going to tell you that your variable is undefined because it doesn't start, because it does start with a capital. And just like this is also different than these. So it's case sensitive. So let's just look at these. This is really important. Variables. A lot of people get tricked with variables. So you have to begin with a letter. If you begin with a number, like if you put 3 discount, the computer thinks that 3 is supposed to be used in a calculation, so it gives you an error because it's expecting like a multiplication sign or an addition sign afterwards. So don't put numbers at the start. You can put a number at the end or in the middle, so you can say discount 1, discount 2, discount 3, but not at the beginning. No spaces at all, because if you put a space, the computer is expecting something to happen new. Like if I put dis space count, it thinks that dis is the variable, and it thinks that count is the variable, and it thinks that there should be something in the middle, like a multiplication sign. And then we can't have any of these special characters because these characters are actually special. We use them for other things. So no special characters. Most programmers use uppercase letters for named constants. So if you're going to have a constant like pi or the tax rate, then keep those capital letters. If you want a space, use an underscore for a space. So this, if I see this in a program, I don't even have to look to see how it's defined. I would know it's a constant because I see that it's capital. So we call that a formatting method to help us read programs better. And if I see something like this, I would know it's a variable without ever even looking to see where it's defined. If constants contain more than one word, separate them with an underscore. If it's a variable when it contains more than one word, then start with a lowercase letter and capitalize the other words. This is not required, okay? Again, this is what we call a way for us to everybody name variables and constants the same. So it's a formatting way that we program in pretty much all languages. I typically see this way of formatting variables and constants in many different languages. So once again, if it's a constant, all capital letters. And if you have two words in a constant, put an underscore to separate the words so it's easy to read. If it's a variable, start, and you have more than one word, start with a lowercase letter, and then the other word should be capital. And I would say this name right here, adjusted gross income, this is really long. I would not name a variable that long. So I would come up with something a lot shorter than that. All right, so this is the same thing that we just talked about. These are all the rules. Okay. Here's some examples of valid names. So gross pay, this is the, we can name a variable gross pay, we can name a variable interest. Here's some good names for constants. Now this one's invalid because it starts with a number, can't start with the number. This is invalid because it has a space, can't have any spaces. This is invalid because it has a period. We can't have periods or any kind of punctuation in our variables. You can have underscores, that's it. We can't use int because int is actually a keyword that you're going to be learning. So it's what we call the reserved word. It's reserved for something. Can't do rate percent because we can't use that special character percent. Okay, so valid, 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 valid. These are constants. Okay. By the way, earlier they talked about something called literal constant and a constant. So a literal constant would be like using the number 4 in my program. If I said multiply 100 times 4, or multiply the variable gross pay times 4, the 4 would be a literal constant. A named constant would be if I take that 4 and I assign it to a constant. So if I say multiply gross pay times, I don't know, the constant a, and a holds the 4, that would be a constant versus a literal constant. Another example would be if I take the cost of my TV, $100, and I multiply it times 0.0825, which is the tax rate, that 0.0825 would be a literal constant. But if I assign that 0.825 to tax rate and define it as a constant, then this would no longer be a literal constant. It would be a named constant because I've given it a name. Okay, so let's look at this problem again that we looked at before. This is the problem where we wanted to calculate the cost of the TV and given the sales tax. So they gave us the sale price, they gave us the sales tax, the sales tax rate, and then we calculate the output, which is the cost of our TV, how much we have to pay. And we had said the first thing we were going to ask the user was to enter the sales price and the sales tax rate. Like if they could enter $100 and sales tax rate of 0.0825. Then we would calculate how much tax they would pay, and then we would calculate the total cost by adding the sales tax and the sale price, and then we would display the cost. So for example, if the price was $2,300 And okay, so the sales tax, they have 0.0 here, but this is obviously wrong. So they have some kind of sales tax rate that gives you $11. Okay, let me see if I can calculate this. 2300 times 0.0. Okay, I'm not sure what the tax rate is, but whatever the tax rate is, you would multiply this times that. It would give you the $11, and your cost would be 240. See, this is totally wrong. Your cost would be $2,311. I don't know what they're doing here. Sorry about that. Go back. So, but let's put some good numbers. So let's say that the TV costs $200, and let's say that my tax rate is 0.03. So I'll multiply 200 times 0.03. That actually gives me a $6, not 1. I don't know why that says 1. And so if it gives me 6, then my cost would be 200 plus 6, would be $206. All right, so what I'm going to do now is we're going to create some variable names. So for sales price, we're going to create a variable called sale price, no space, lowercase s, capital P. For sales tax rate, we'll create a variable called tax rate, and lowercase t, capital R. For sales tax, this is what you end up paying. Like, let's say you end up paying $5 in sales tax, then this would be SALES, capital T, no space, AX. And then cost would be COST. So this is if we created variables for all of these. So earlier we said that memory locations come in different types and sizes. So here are the different types of memory of data types that we have in C++. These are called primitive or built-in data types. So primitive or built-in data types because these are keywords or reserved words. We can also create our own data types if we wanted. So that's something else that you could do. You would probably do in advanced C++, but not in this class. So the data types are short, integer. A short is it's less than an integer. Integers are whole numbers. Let me see if I have a table. Yeah, here's our table. So you have a short, which is an integer, and here's the range. So it goes from negative 32,768 to positive 32,767, and it takes up 2 bytes in memory. Remember that 1 byte equals 16 bits. So this is 32 bits. An integer, this is the range of an integer, so it's a pretty big number. It doesn't have any decimal numbers. It takes up 4 bytes. But even if you put the number 2 into an integer, you're taking up 4 bytes for the number 2. Okay, just so you know. So you might want to use a short for numbers like between 1 and 100. We have float. A float is can have decimal numbers. Doubles can also have decimal numbers, but doubles are just, you can have bigger numbers. So here's the size, 4 bytes, 8 bytes. So for most everything that you do, you could stick with a float. It's 4 bytes, for averages and things like that. You're not going to have any bigger numbers than this. Then we have booleans. Boolean is a true or false value, so it would be a 1 or a 0. So 1 and 0 are true and false, and this is 1 byte. And Boolean is 1 byte. So we typically use Booleans, for example, if we say, okay, if he pressed enter, is that true or false? Did he press enter or not? And then we have one character is 1 byte. A character would be like the letter A, and then a string, 0 or more characters. So 0 or more characters, string would be like a name without spaces. So strings do not have spaces. So like the name, my last name Serrano would be a string. So these are our most commonly used data types. So we'll go back here and, so one thing, looking at this here, let's take a look at this, just see if I forgot anything. So Boolean stores true and false. We said short and integers, numbers without decimal places, float and doubles are real numbers, so they have decimal places. The one thing, so earlier I said characters would be something like the letter A, but really it's any character that you see on your keyboard. It can be a letter, it can be a symbol, or it can be a number. So a number, like the number 2, if you define it as an integer, then you can use it to add and do mathematical equations. But if you defined the number 2 as a character, then all you can do is print it out, display it, add it to strings, but you cannot use it in mathematical equations. And then you have strings as a data type. It can store 0 or more characters. All right, so going back to our problem that we had earlier, we have these variable names, and now we have the data type that they chose. So they chose to define these as doubles, all these variables. And they chose double because double, remember, can have a decimal number. And I guess they, want to choose the biggest data type just in case they have a really, really, really big cells amount, then you have enough space for the calculation. All right, so numbers represented in internal memory using binary base 2 number systems, which are the digits 0 and 1. We're used to the decimal base 10 number system, which is 10 digits 0 through 9. But when we store something in internal memory, we're storing it with zeros and ones. And the compiler is actually the one that translates everything and changes it into a binary number system. Character data is stored using ASCII code. We'll look at what ASCII and binary looks like. So earlier I was saying how 8-bit codes, or 1 bit equals 1 byte equals 8 bits, and each bit is either a 0 or a 1. Upper and lowercase versions of letters have distinct codes, and the computer distinguishes between numbers and ASCII codes based on data type. So let's take a look at what that looks like, because it's probably confusing. So here's a chart that you'll always see in every programming book, and this chart has these characters here. So you have 0 through 9, colon, semicolon, capital A, capital letters, and lowercase letters. So this would be the ASCII code for this number, and this is the binary code for that number. And capital A has an ASCII code of 65, and this is the binary code, etc. I'm going to post another video that talks a lot about how to convert into binary. If you're interested, and I think it'd be a good video for you to know. We don't go deeply into conversions in this class, but it's just interesting to see how to convert numbers to binary. Okay, so setting an initial value for a variable or named constant is called initializing. And like I said earlier, when you get a mailbox, you want it to be empty. We typically initialize our values to something that's empty. It's required for constants. It is recommended for variables. Memory locations are usually initialized with the literal constant. Data type of literal constant should match the data type of memory locations. So what does that mean? Well, that means that if I have an integer, and the integer is age, then I should initialize it to a 0. If I have tax rate and it's a constant, then I should initialize it to the actual tax rate, 0.0825 or whatever it is. Numeric literal constants initialize short, int, float, and double data types. Can contain digits 0 through 9, plus, minus, period, and E for scientific notation. Literal constants initialize char data types consist of one character in single quotation marks. Strings of more than one character has quotes. So let's take a look at some examples, hopefully. Let me see. Okay, let's look at this one. So sales price, double, we would initialize it to 0.0. If this were an integer, then we would initialize it to just a 0. If this was a char, then we would initialize it to single quote, open single quote, close single quote. So variables and named constants are declared using C++ instruction, and these are a lot of words. I just want to get to, okay. So you can read the other ones that I skipped. You can read those. You have the PowerPoint. I'm going to get to how to do this. So we're talking about initializing our variables. So here's an integer. We initialize it to 0. Here's a double. Initialize it to 0.0. A Boolean is initialized to true. This is a keyword. Char, initialize it to, you have a single quote, space, single quote. A string, you have 2 double quotes, nothing in between. That's how we initialize our variables. And the other thing to look at is this is the actual statement in C++. So you have data type, then you have the name of the variable, you have an equal sign, you have the initializing value, and then you have a semicolon. Each statement in C++ has to end in a semicolon. If you don't have a semicolon, you're going to get an error. So here is how we declare our values for our program. Here's an example of using named constants. So if you want to declare a named constant, you have to use a keyword called const, then the data type, then the name of the named constant, equal sign, the value, and semicolon. It's a constant, so you have to give it a value. And from then on, you can never change while the program is running. Pi cannot change, min age cannot change. None of these can change because they're constants. So somewhere in your program, you can use these, like you can print the name of the bank, but you can't change it. You can use pi in calculation, but you can't change it. So this word here lets the compiler know, okay, I'm going to see a constant, I'm going to see a value for the constant. So notice, if you have variables, don't ever assign any values to variables. I will take off points. Variables should always be assigned a 0 or a 0.0 or empty quotes because they're variables. Okay, so that's the end of this chapter, and this here's the main thing that you have to know. For your lab assignment, you're going to create variables and you're going to create constants, and you have to have both of them. So each problem will require you to have some constants and some variables. So make sure that you figure out which ones are the constants. Make sure that you define the names correctly and give it the correct values. Always 0 for variables, always some kind of value for constants. All right, good luck with your lab. Thank you.